how do we capture infinity in a simple fraction? In this video, we'll first master the shortcut for recurring decimals, and then explain the proof behind it. Let's get started. To master the shortcut, we first categorize recurring decimals into two types, pure and mixed. Pure recurring decimals, like 0.7 recurring, begin the pattern immediately after the decimal point. Mixed recurring decimals, like 0.463 recurring, have one or more fixed digits before the repeating pattern begins. For pure recurring decimals, the rule is straightforward. The numerator is the repeating pattern itself, and the denominator consists of a 9 for every repeating digit. Let's take 0.7 recurring. We have just one digit repeating, which is 7. So 7 goes on top. And because it's only one repeating digit, we just put one 9 at the bottom. The result is 7/9. What if 3 digits repeat? In this case, the pattern is 325, so that's our numerator. Since there are 3 repeating digits, we place 3 9s in the denominator. Simple as that. Now, for mixed recurring decimals, the formula gets slightly more involved. The numerator is the total digits minus the fixed part, and the denominator is a combination of 9s and 0s. Let's try this with 0.463 recurring. First, the numerator, take the whole number 463 and subtract the fixed part, which is 4. For the denominator, we use 2 9s for the repeating digits and 1 0 for the fixed digit. Job done. Let's have a look at this one. The numerator is the whole value minus the non-recurring part. Since we have 1 recurring digit and 2 fixed, the denominator is a 9 followed by 2 zeros. Easy. Now, let's reveal the algebraic proof behind the shortcut, starting with pure recurring decimals. First, we let x equal the recurring decimal. It's important to remember that this x is the final value we are looking to find. But to solve for x, we need to deal with that infinite tail. So, let's create a second equation. Since one digit repeats, we multiply both sides by 10. The goal here is to shift the decimal point so that we have a second equation with the exact same repeating tail. You might wonder, could we multiply by 100 or 1000 instead? Well, as long as the repeating parts align, they will still cancel out, and the final result will be exactly the same. Now for the clever part, by subtracting the original equation from this new one, we can completely eliminate those infinite decimals. This leaves us with 9x equals 7, which proves why our denominator is always 9. Now, let's explore mixed recurring decimals, where the repeating pattern doesn't start immediately after the decimal point. Let's start by representing our decimal as x. But in this case, a single multiplication isn't enough to get the decimal parts to match up. To fix this, we need to create two new equations where the recurring parts are perfectly aligned. First, we multiply by 10 to shift the decimal point so the repeating pattern starts immediately. Next, we multiply the original equation by 1000 to create a second equation with the same repeating tail. Now, we subtract the smaller equation from the larger one. The entire infinite tail simply vanishes. This leaves us with a fraction, which we can then divide down to its simplest form to reach our final answer. That covers everything for today. Have you got it? For more insights and in-depth content, subscribe to Scholar Formula. I'll see you in the next lesson.